Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of our universe, there exist regions so dense and gravitationally powerful that nothing, not even light itself, can escape their grasp. These are black holes, perhaps the most mysterious and fascinating objects in all of cosmology. To understand what makes a black hole so extraordinary, we must first grasp the fundamental concept that governs their existence: gravity. When a massive star, typically 8 to 25 times more massive than our Sun, reaches the end of its nuclear fuel supply, it faces a catastrophic collapse. The star's core, no longer supported by the outward pressure of nuclear fusion, succumbs to its own gravitational pull. This collapse happens in mere seconds, creating a density so extreme that a teaspoon of this material would weigh as much as Mount Everest. At the heart of every black hole lies what physicists call a singularity, a point where density becomes infinite and the known laws of physics break down. Surrounding this singularity is the event horizon, a spherical boundary that marks the point of no return. The radius of this boundary, known as the Schwarzschild radius, depends entirely on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of approximately 3 kilometers. The mathematics behind black holes emerged from Albert Einstein's general theory of relativity, published in 1915. German physicist Karl Schwarzschild solved Einstein's field equations just months after their publication, describing the space-time geometry around a massive, non-rotating object. Schwarzschild's solution revealed that sufficiently massive objects could create such extreme curvature in space-time that escape becomes impossible. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The classification of black holes depends primarily on their mass. Stellar mass black holes formed from collapsed stars typically range from 3 to 20 solar masses. Intermediate mass black holes, though rare and difficult to detect, may contain hundreds to thousands of solar masses. At the extreme end are supermassive black holes, containing millions to billions of solar masses, residing at the centers of galaxies. What makes black holes particularly intriguing is their effect on surrounding matter. As material spirals inward, it forms an accretion disk, heating to temperatures exceeding 1 million degrees Celsius. This superheated matter emits intense radiation across the electromagnetic spectrum, making black holes paradoxically among the brightest objects in the universe despite their inability to emit light directly. The concept of black holes challenges our understanding of space and time. Near the event horizon, time itself becomes distorted due to gravitational time dilation. An outside observer would see time slow dramatically for objects approaching the black hole, while the infalling observer experiences time normally until reaching the singularity. Modern astronomy has confirmed the existence of black holes through various observation methods. The first indirect evidence came from studying X-ray emissions from binary star systems where invisible companions strip material from visible stars. The discovery of gravitational waves by the Laser Interferometer, Gravitational Wave Observatory, or LIGO, in 2015, provided direct confirmation when it detected the merger of two stellar mass black holes. The study of black holes continues to push the boundaries of physics, connecting quantum mechanics with general relativity in ways that may unlock new understanding of the universe's fundamental nature. These cosmic giants serve as natural laboratories for testing the most extreme conditions possible, where the familiar rules of physics reach their limits and new discoveries await. The birth of a black hole represents one of the most violent and energetic events in the universe, marking the spectacular death of a massive star. To understand this process, we must follow the complete life cycle of stellar evolution, from the nuclear furnaces that power stars to the catastrophic collapse that creates these gravitational monsters. Stars spend most of their lives in a delicate balance between two opposing forces: the inward pull of gravity, trying to collapse the star, and the outward pressure generated by nuclear fusion in the core. For stars like our Sun, this balance can persist for approximately 10 billion years. However, for massive stars, those containing at least 8 solar masses, this equilibrium is far more precarious and short-lived. The nuclear fusion process in stellar cores follows a predictable sequence. Hydrogen fuses into helium, releasing tremendous energy that maintains the star's structure. When hydrogen becomes depleted, the core contracts and heats up enough to begin fusing helium into carbon and oxygen. This process continues through successive stages: carbon burning, neon burning, oxygen burning, and finally silicon burning, which produces iron. Iron represents a critical threshold in stellar nucleosynthesis. Unlike lighter elements, iron cannot release energy through fusion. Instead, it absorbs energy. When a massive star's core becomes dominated by iron, typically reaching a mass comparable to our Sun, but compressed into a sphere only 20 kilometers, across the nuclear fire that has sustained the star for millions of years, suddenly extinguishes. Without the outward pressure from fusion reactions, gravity wins decisively. The core collapse happens with breathtaking speed. The entire process takes less than 1 second. During this collapse, the core's density increases so rapidly that protons and electrons are forced together to form neutrons, releasing an enormous burst of neutrinos that carry away 99% of the explosion's energy. The collapse continues until nuclear forces create a rebound effect, generating a massive shock wave that propagates outward through the star's outer layers. This creates a supernova explosion, one of the most energetic events in the universe, briefly outshining an entire galaxy containing hundreds of billions of stars. The fate of the stellar core depends critically on its mass after the supernova explosion. If the remaining core mass is between approximately 1.4 and 3 solar masses, known as the Tolman-Oppenheimer-Volkoff limit, the collapse halts when nuclear forces provide sufficient pressure to support the core as a neutron star. These incredibly dense objects pack more mass than our Sun, into a sphere roughly 20 kilometers in diameter. However, if the core exceeds approximately 3 solar masses, no known force can halt the gravitational collapse. The core continues shrinking past the neutron star phase, becoming increasingly dense until it forms a singularity, a point of infinite density where space-time curvature becomes infinite, and the laws of physics as we know them cease to apply. The hue, formation of the event horizon, occurs when the collapsing matter reaches the Schwarzschild radius. At this point, the escape velocity equals the speed of light, making escape impossible even for electromagnetic radiation. The newly formed black hole settles into its final configuration within milliseconds, though the surrounding supernova explosion continues expanding for thousands of years. Recent observations have revealed that some massive stars may collapse directly into black holes without producing visible supernovae called failed supernovae or collapses. In these cases, the core collapse proceeds so efficiently that the shockwave never reaches the surface, and the entire star simply disappears behind its newly formed event horizon. The mass of the resulting black hole depends on the original star's mass and the amount of material ejected during the supernova. Stellar mass black holes typically range from 3 to 20 solar masses, though recent gravitational wave detections have revealed black holes with masses up to 100 solar masses, suggesting that either more massive stars can form black holes or that black holes can grow significantly after formation through accretion or mergers. Albert Einstein's general theory of relativity, published in 1915, fundamentally revolutionized our understanding of gravity, space, and time. Rather than viewing gravity as a force acting between objects, Einstein proposed that massive objects actually curve the fabric of space-time itself. This radical concept predicted phenomena so extreme that Einstein himself initially doubted whether black holes could actually exist in nature. The mathematical foundation for black holes emerged from Carl Schwarzschild's solution to Einstein's field equations, derived while Schwarzschild served on the Russian front during World War I. Tragically, Schwarzschild died of illness just months after making this groundbreaking contribution, never knowing that his work would describe some of the most exotic objects in the universe. Schwarzschild's metric describes the curvature of spacetime around a spherically symmetric, non-rotating, massive object. The solution revealed that at a critical radius, now called the Schwarzschild radius, spacetime becomes so severely curved that escape becomes impossible. For decades, physicists debated whether this mathematical singularity represented a real physical phenomenon or merely an artifact of the coordinate system used. One of general relativity's most striking predictions concerns the behavior of time near massive objects. Gravitational time dilation means that time passes more slowly in stronger gravitational fields. Near a black hole's event horizon, this effect becomes extreme. An observer watching someone fall toward a black hole would see the falling person's clock running increasingly slowly, their image becoming progressively redder and dimmer as gravitational effects stretch light waves to longer wavelengths. From the perspective of the falling observer, however, time passes normally. They would experience crossing the event horizon in finite proper time, though they would be torn apart by tidal forces, the difference in gravitational pull between their head and feet, long before reaching the singularity. This stretching effect, colloquially known as spaghettification, demonstrates how extreme gravity distorts not just spacetime, but matter itself. Einstein's equations also predict frame dragging, or the lens-Thirring effect, where rotating massive objects literally drag spacetime around with them. For rotating black holes, described by the Kerr metric derived by Roy Kerr in 1963, this creates an ergosphere, a region outside the event horizon where spacetime itself rotates, making it impossible for any object to remain stationary relative to distant observers. The first observational confirmation of Einstein's gravitational theories came through precision measurements of Mercury's orbital precession, which matched general relativity's predictions perfectly. However, direct evidence for black holes required decades of technological advancement and careful astronomical observation. The breakthrough came with X-ray astronomy in the 1970s. The first strong black hole candidate, Cygnus X1, was identified through its X-ray emissions as it stripped material from a companion star. The infalling matter, accelerated to tremendous speeds and heated to millions of degrees, produces characteristic X-ray signatures that match theoretical predictions for black hole accretion disks. Gravitational wave detection by LIGO represents perhaps the most dramatic confirmation of Einstein's predictions. On September 14, 2015, LIGO detected ripples in spacetime itself, created by the merger of two black holes approximately 1.3 billion light-years away. This detection not only confirmed the existence of gravitational waves, predicted by Einstein a century earlier, but also provided direct evidence for black hole mergers and their properties. The Event Horizon Telescope project achieved another milestone in 2019 by capturing the first direct image of a black hole's shadow. The supermassive black hole at the center of galaxy Messier 87, containing 6.5 billion solar masses, appeared exactly as general relativity predicted, a dark shadow surrounded by a bright ring of hot, glowing matter. More recently, observations of stars orbiting the supermassive black hole at our galaxy's center, Sagittarius A star, have provided exquisite tests of general relativity in the strong field regime. These observations have confirmed gravitational redshift, orbital precession, and other relativistic effects with unprecedented precision. Each new observation continues to validate Einstein's century-old predictions with remarkable accuracy, demonstrating that general relativity remains our best description of gravity's behavior, under the most extreme conditions nature can provide. At the heart of nearly every large galaxy in the universe lurks a supermassive black hole, containing millions to billions of times the mass of our Sun. These galactic monsters play a fundamental role in shaping the evolution and structure of their host galaxies, regulating star formation and influencing cosmic evolution on the largest scales. Understanding these giants requires examining both their formation and their ongoing impact on the universe around them. The existence of supermassive black holes presents a significant puzzle in astrophysics. Unlike their stellar mass cousins, which form from the collapse of individual stars. Supermassive black holes appear to have existed when the universe was very young. Observations from the James Webb Space Telescope, or JWST, have revealed fully formed supermassive black holes less than 1 billion years after the Big Bang, suggesting they must have grown to enormous sizes incredibly quickly. Several competing theories attempt to explain their rapid formation. The first proposes that supermassive black holes grew from stellar mass seed black holes through continuous accretion of surrounding matter. However, calculations suggest this process would require nearly perfect conditions and extremely efficient growth rates to reach the observed masses so early in cosmic history. Alternative theories suggest more exotic formation mechanisms. Intermediate mass black holes, containing hundreds to thousands of solar masses, might form directly from the collapse of the first generation of massive stars or from the gravitational collapse of dense stellar clusters. These intermediate objects could then merge and grow through accretion to become supermassive black holes. The most intriguing possibility involves direct collapse scenarios, where massive clouds of primordial gas in the early universe collapse directly into supermassive black holes without first forming stars. This process would require specific conditions, including the absence of heavy elements that would normally allow gas clouds to cool and fragment into stars, but could potentially explain the existence of billion solar mass black holes in the young universe. When supermassive black holes actively accrete matter, they become among the most luminous objects in the universe. The infalling material forms a massive accretion disk, heating to temperatures exceeding 10 million degrees Celsius, as gravitational potential energy converts to thermal energy. This process can be extraordinarily efficient, converting up to 42% of the infalling matter's rest mass into energy, far more efficient than nuclear fusion. Active galactic nuclei, or AGN, represent galaxies whose central supermassive black holes are actively feeding. These objects exhibit enormous luminosities, often outshining their entire host galaxy, containing hundreds of billions of stars. Quasars, the most luminous class of AGN, can be detected across cosmological distances, serving as beacons visible from the early universe. Many active supermassive black holes launch powerful jets of plasma traveling at speeds approaching the speed of light. These relativistic jets, extending thousands of light years from the black hole, are believed to be powered by the extraction of rotational energy from spinning black holes through magnetic field interactions, a process described by the Blandford-Znajek mechanism. The relationship between supermassive black holes and their host galaxies reveals remarkable correlations. The M-sigma relation demonstrates that black hole mass correlates strongly with the velocity dispersion of stars in the galactic bulge, suggesting a fundamental connection between black hole growth and galaxy formation. Similarly, black hole mass correlates with total galaxy mass, indicating coevolution over cosmic time. Supermassive black holes serve as cosmic thermostats, regulating star formation in their host galaxies through feedback mechanisms. When actively accreting, they heat surrounding gas through radiation and outflows, potentially halting star formation. Conversely, their jets can compress gas in some regions, triggering star formation while suppressing it elsewhere. Recent observations have revealed that most supermassive black holes spend most of their time in a quiescent state, accreting matter at very low rates. Our own galaxy's central black hole, Sagittarius A star, containing 4.1 million solar masses, exemplifies this quiet phase, though occasional feeding events cause temporary brightening as stars or gas clouds venture too close. The study of supermassive black holes continues revealing their central importance in cosmic evolution, connecting the physics of extreme gravity with the large-scale structure and evolution of the universe itself. Black holes represent the ultimate testing ground for our understanding of fundamental physics, where the extreme conditions push theoretical frameworks to their absolute limits. These cosmic laboratories provide unique opportunities to explore the intersection of quantum mechanics and general relativity, potentially revealing new physics that could revolutionize our comprehension of reality itself. Stephen Hawking's groundbreaking work in the 1970s revealed that black holes are not completely black. Through a quantum mechanical process now called Hawking radiation, black holes actually emit thermal radiation and slowly evaporate over time. This discovery emerged from applying quantum field theory to curved space-time near the event horizon, where virtual particle pairs can become real through gravitational effects. The process works through quantum fluctuations that continuously create particle-antiparticle pairs throughout space. Near a black hole's event horizon, one particle from such a pair can fall into the black hole, while the other escapes, effectively extracting energy from the black hole's mass. The temperature of this radiation is inversely proportional to the black hole's mass. Stellar mass black holes emit radiation with temperatures of approximately 10 to the -7 Kelvin, far colder than the cosmic microwave background. This discovery leads to the black hole information paradox, one of the most profound puzzles in modern physics. Quantum mechanics demands that information cannot be destroyed, yet classical general relativity suggests that anything falling into a black hole, including all information about its quantum state, is lost forever when the black hole eventually evaporates through Hawking radiation. Resolving this paradox requires understanding how quantum mechanics and gravity interact at the most fundamental level. Several proposed solutions challenge our basic assumptions about space-time and information. The holographic principle suggests that all information contained within a volume of space can be encoded on its boundary surface, implying that information falling into black holes might be preserved in some form on the event horizon. String theory approaches the problem through the ADC-CFT correspondence, a mathematical duality that relates gravity in higher dimensional spaces to quantum field theories on their boundaries. This framework suggests that black hole interiors might be emergent phenomena rather than fundamental aspects of space-time geometry. Recent theoretical developments propose that black holes might be connected through Einstein-Rosen bridges, or wormholes, creating shortcuts through space-time. The ER equals EPR conjecture suggests a deep connection between quantum entanglement and space-time geometry, potentially explaining how information might be preserved during black hole evaporation. Black holes also provide natural laboratories for testing theories of quantum gravity. The singularity at a black hole's center represents a breakdown of general relativity, where quantum effects of gravity likely become important. Understanding this regime requires a theory of quantum gravity, the holy grail of modern theoretical physics that would unify quantum mechanics with general relativity. Loop quantum gravity proposes that space-time itself is quantized at the smallest scales, potentially resolving singularities by preventing infinite density. Alternative approaches like emergent gravity suggest that gravitational effects arise from more fundamental quantum processes, similar to how thermodynamic properties emerge from statistical mechanics. Observational advances continue providing new insights into black hole physics. Gravitational wave detections reveal properties of black hole mergers, including tests of general relativity in the strong field regime and measurements of black hole spins. The Event Horizon Telescope project plans to study the immediate vicinity of black holes with unprecedented resolution, potentially observing relativistic effects and testing theoretical predictions. Future space-based gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, will detect mergers of supermassive black holes, providing information about galaxy formation and the growth of the earliest black holes. These observations may reveal deviations from general relativity or discover new types of compact objects. The study of black holes continues pushing physics toward a more complete understanding of nature's fundamental laws. Whether through resolving the information paradox, developing quantum gravity theories, or discovering new phenomena through observation, black holes remain at the forefront of humanity's quest to understand the deepest mysteries of existence. As we stand on the threshold of revolutionary discoveries, black holes serve as cosmic beacons, guiding us toward new physics that could transform our understanding of space, time, matter, and information itself.